Let's explore how increasing the tension in a string affects the speed of waves traveling through it. When a wave travels through a string, the tension in that string plays a crucial role in determining how fast the wave moves. First, let's understand what determines the speed of a wave in a string. The speed of a wave through any medium depends on the physical properties of that medium. The wave speed equals the square root of tension T divided by linear mass density mu. T represents the tension force in the string, measured in newtons. Mu is the linear mass density, which is the mass per unit length of the string. Here we see a string with tension forces pulling at both ends, and the linear mass density represents how much mass is distributed along its length. Now let's examine exactly how tension affects wave speed. Wave speed is proportional to the square root of tension. This means when we increase the tension in the string, the wave speed increases. However, this relationship is not linear. It follows a square root pattern, meaning doubling the tension does not double the speed. This graph shows the square root relationship between tension and wave speed. As tension increases, speed increases but at a decreasing rate. Let's understand the physics behind why tension affects wave speed this way. When we increase tension, we create stronger restoring forces that pull disturbed parts of the string back to equilibrium faster. These restoring forces act to straighten the string, and stronger tension means stronger forces pulling each segment back to its rest position. With higher tension, particles in the string respond more quickly to disturbances, allowing the wave to propagate faster. Let's work through a practical example with real numbers. Consider a string with a linear mass density of 0.01 kilograms per meter. Our linear mass density is 0.01 kilograms per meter. In the first case, we apply a tension of 4 newtons. The wave speed equals the square root of 4 divided by 0.01, which gives us 20 meters per second. Now let's increase the tension to 16 newtons, which is 4 times greater than before. The new wave speed equals the square root of 16 divided by 0.01, which gives us 40 meters per second. Notice that quadrupling the tension only doubled the speed, demonstrating the square root relationship. This comparison clearly shows how a 4 times increase in tension results in only a 2 times increase in wave speed. This principle has many important real-world applications. In musical instruments like guitars and violins, tightening strings increases the wave speed, which raises the pitch of the sound produced. In power transmission lines, maintaining proper tension ensures that mechanical waves from wind or disturbances travel at controlled speeds. This diagram shows how the same wave travels faster through a string with higher tension compared to lower tension. Let's summarize what we learned about tension and wave speed. The fundamental equation, wave speed equals the square root of tension divided by linear mass density. Increasing the tension in a string always increases the speed of waves traveling through it. The relationship follows a square root pattern, so doubling tension increases speed by the square root of 2. This occurs because higher tension creates stronger restoring forces that return disturbed portions of the string to equilibrium faster. Understanding this relationship is fundamental in musical instruments, engineering applications, and wave physics in general.